Hello all, good morning. Welcome to Unacademy. Today we will going to see our next lecture on discrete mathematics. Okay. Here, before going to start this, let me introduce myself. Myself, Dhanashree Mam. I completed my MSc in mathematics from Mumbai University and also having 13 plus years of teaching experience. I mentored more than 10,000 plus students for the engineering. Now here I will tell you how to install the Unacademy's learning app. See, here go to your mobile's Play Store app, then search Unacademy's learning app, and after that go here and press the install button. Right, next step is to manage your goal. जैसे कि हम लोग यहाँ पे अभी GATE and ESE के लिए पढ़ रहे हैं, so you can manage your goal here. Then next, then after that place the Get subscription button icon to get the subscription of Unacademy's. Next. Step is here you can take your subscription plan either for 12 months or 24 months, or you can use the promo code to get the 10% discount on your subscription fees. You can use my promo code, that is DSP, to get the 10% discount on your subscription fees. After that here you can manage your goal. After that you can manage your goal here, and you can now here can pay your subscription fees by using any one of these methods, either by debit card, credit card, EMI, or UPI, wallet pay, net banking, anything. It is up to you. Now, most important thing is that you can use my promo code DSP to get the 10% discount on your subscription. Okay, जैसे कि आप लोगों ने अभी देखा है, हमने just before going to start this lecture, the first introductory slide you have seen that the Unacademy का YouTube festival चालू हो रहा है आज से. So yes, you can crack and get by use with the help of top educators teaching live on Unacademy, and which starts from batch for batch A for GATE 2022. You can see here your batch. Okay, it starts from 18th of January, English batch, with can see the faces here, which is very commonly faces every time you will see on the Unacademy's platform, that is Ankit sir, by Reddy sir, by Shankar sir, and everybody is here can crack it your GATE exam for 2022 with the help of all these educators, top educators of Unacademy. Now next is also the same, the batch for A for GATE 2022. It also starts from 18th of January, that is for ECE, and work for GATE 2023. Now actually you are starting your preparation for the GATE exam 2023 from right now, which is the batch starting from batch A starts from 18th of January. So please be enrolled your roll numbers here. So work your GATE 2023 for EE batch A English starting from 18th of January. So early start, extra age. So, and the most important thing, to unlock the free plan of Unacademy, you can use my promo code DSP for the special classes, for the live test series, and for quiz and Unacademy combat. Okay. Now this is our 12th lecture on discrete mathematics. In previous 12 lectures, I have completed most of the topic from your discrete mathematics, that is sets, relation versus algorithm, everything we have covered, mathematical logic, and everything we have already covered it. That now the next topic of the this theory, that is group theory. Yesterday we have seen our whole 2 hours lecture. Yesterday we have seen how to show that it is a group and everything. I just recall the 1, 2 or more sentences of group, how to prove that group. To prove that any set is a group, we have to prove that the 5 postulates, or for abelian group we have to prove that the 5 postulates. Here first postulates to prove that it is group is closure property, right? Just I'm recalling it. Closure property. So what do you mean by closure property? If you take any 2 elements from that set, so algebraic structure A, G star is said to be a group. if it satisfies the closure property. For any two elements belongs to G, then A star B is also belongs to G. It means G is closed with respect to the defined operation star. You can see it here. And second property is associative property. Yesterday we have seen many examples on these groups. Okay, with the different, the set is same, but if you define the operation differently, then you will get the different properties here. Closure property, associative property, existence of identity, existence of inverse, everything we can see here. And also we prove that the set is group. Now after that, in this lecture we will see how to prove the subgroups. First of all, we will see the definition of subgroups, then normal subgroups, cosets, and homomorphism. Everything we will cover today in this lecture. So subgroups. So first of all, we will see that the definition of a subgroup. Let's suppose G star is a group and H is a subset of G. That is, H is a subset of G, and H star is also a group. Then H star is known as subgroup of G. Okay, so can you give me the one example? As we have seen yesterday, two different sets with the defined different operation, it is also a group. So here we can say that G star is a group and H is a subset of G, and H star is also a group. Then H star is known as subgroup of G. It means you say that here H is a subgroup of G when H is also a group with respect to the defined operation star. Now for example, here you can see that, for example, suppose here, as we know that Q plus set of rationals with defined operation addition forms a group, right? Forms a group. As we have seen yesterday, how to prove that it is a group. Closure property is also satisfied in the set of rational numbers. For any two rational number, addition of two rational number is again a rational number. Then associativity A plus B plus C is same as A plus B plus C. So here associativity also holds, and there exists an identity element. 0 belongs to set of rational number which acts as an identity element for the set of rational numbers. Okay. Similarly, there exists an inverse of the element, that is minus of A belongs to Q, acts as an inverse of A, right? Minus A belongs to Q, acts as an inverse of A here. So A plus minus A is equal to identity, that is A plus minus A is equal to 0. So you will get that identity here. Now, fifth one is an Q plus is an abelian group. Commutative property also holds in set of rationals with respect to addition. That is A plus B is same as B plus A, right? So here commutative property also holds. So Q plus forms a abelian group. Okay. Now here, which is subset of this? So as we know that Z is a subset of Q, set of integers is a subset of set of rationals, right? So set of integers is a subset of rationals, and set of integers with respect to addition also forms a group. Okay, also forms a group. So set of integers with respect to addition also forms a group, which implies here that Z is a subgroup of Q plus. Z plus is a subgroup of Q plus. See here, I'm not showing that here Z plus is a forms a group, because yesterday's lecture you go through my previous lecture and you can see that group, that is groups and examples, you will get that link. And here Z plus also forms a group. I explained there Z plus, how Z plus forms a group, that lecture, so you can go through it. And here directly I am saying here Z plus is a group, therefore Z plus is a subgroup of Q plus, as Z is a subset of Q, so therefore Z plus is a subgroup of Q plus. So there are many definitions. You can say that here subgroup, suppose here also Z plus is a subgroup of R plus, because Z is a subset of R, so you can prove it here. Okay, this is a simple definition, but we will see the most next definition or criteria, that is if G star is a group. Now to check whether it is subgroup or not, we will see that this is if the criteria satisfied, if this criteria is satisfied of the subgroup. If G plus G star is a group and H is a non-empty subset of G, then H is a subgroup of G if and only if for all AB belongs to H, which implies A star B also belongs to H. For all A in H, which implies A inverse belongs to H, where A inverse is the inverse of A in G. right? For all AB belongs to H, which implies A star B belongs to H. For all A belongs to H, which implies A inverse belongs to H, then where A inverse is the inverse of A in G. So keep it in mind. It means it must satisfy all the property. To get the inverse, it must have to satisfy the existence of identity. Without getting identity element, you can't find out inverse. So it means obviously it is here if both the properties are satisfied. It means if these two properties are satisfied, then H is a subgroup of G. And if H is a subgroup of G, then it must satisfy these two properties. Okay. I hope you are getting it clear here. The existence criteria here. So we can prove that here. AB belongs to H, then A star B or A star B also belongs to H. So here we can say that for all AB belongs to H, A star B belongs to, then AB inverse also belongs to H. Okay. So here this is the necessary condition for the group. Suppose H star is a necessary condition, so we will prove it here. Suppose H star is a subgroup of G. Suppose H star is a subgroup of G star, right? H star is a subgroup of G star, then H star itself, H star itself is a group, and hence H is closed, and hence H is closed with operation star. Okay. Suppose H star is a subgroup of G star, then H star is itself is a group, and hence H is closed with respect to star, right? So that is for AB belongs to H, which implies H star B also belongs to H. As H is a, see, H star is a subgroup of G, then H star is itself a group, right? By definition of a subgroup. So it must be a group, and as it is a group, so it must satisfy the closure property. So if you take any two elements in H, that A star B also belongs to H by closure property. Also for every element, also for every element, also for every element A belongs to H, there exists A inverse in H such that A star A inverse, which is equal to identity, is also belongs to, it means identity is also belongs to H here. Okay. Now the next property we will see here, the condition. Second condition, sufficient condition. This is necessary condition, sufficient condition. Suppose assume that it is a subgroup. So these two properties are satisfied, and we have to prove that H is a group. H with respect to star is a group. So first we will see that the conditions are sufficient. Conditions are sufficient. Okay. So for first is closure property. Here now we assume that the second part, for all AB belongs to H, A star B belongs to H, and this A inverse also belongs to H. Okay. So here we already used H is a subgroup of G, then these two properties are satisfied. Yes. Now the second part is we will assume that these two are true, then we will prove that H is a subgroup of G. Okay. So here for closure property, first to prove that any set is a group, it is must have to satisfy first four properties: closure property, associative, existence of identity, and existence of inverse, right? So here we will see that the closure property, for closure property to prove that H is a subgroup of G, for that we have to take two elements from H. For A belongs to H, B belongs to H, which implies A star B also belongs to H by our assumption, as these two properties are satisfied, right? So A star B belongs to H, therefore H is closed with respect to star. Therefore H is closed with respect to star. Now second property, that is associative property. Associative property. Right? For that we require, now the elements of H are also elements of G, and G is a group, so which implies associativity also holds in H. Okay. So the elements of H, and right here, the elements of H are also are also elements of G, the composition star in G is associative. Therefore, the same composition must also be associative in H. Okay. Now third one, here we can see that the third one, add some slides. Also associative in H. Now third one is existence of identity. Right? Existence of identity. The identity element of the subgroup is same as identity element of the group. Identity element of the group. As G is a group, what we'll get? A belongs to H, which implies A inverse belongs to H, as it is given. A belongs to H, A inverse also belongs to H. For any two elements, A belongs to H, B belongs to H, then AB inverse belongs to H. Right? So for that here, A belongs to H, A inverse belongs to H. So closure property A star A inverse, which is equal to A inverse star A is equal to E. So identity also belongs to H. Therefore, E is then identity element of H. Therefore, then identity element of H. Right? Now, fourth property, that is existence of inverse. Right? Since A belongs to H, which implies A inverse also belongs to H. Therefore, each element necessary part, to prove that the necessary part here will be, let's see, necessary part, that part we will see here. If H star is a, no, if H star is a subgroup of G star, then H star the subgroup of G star. H star is a subgroup of G star, then H star itself a group, right? Then H star itself is a group. H star is itself a, right? Now, and if B belongs to H, which implies B inverse, then inverse also exists in H, right? If B belongs to H, then B inverse also belongs to H. Also, for AB belongs to H, which implies AB inverse also belongs to H. Okay. Now AB inverse belongs to H, which implies A star B inverse also belongs to H. Right? Hence AB belongs to H, which implies A star B inverse also belongs to H. Therefore, the condition is necessary. Okay, this condition is necessary for the subgroup. Now, next is sufficient part. We will see the sufficient part also. Sufficient part. Here, you can see. Now it is given that. Now it is given that. Second part. It is given that here A belongs to H, B belongs to H, which implies A star B inverse also belongs to H. Then we have to prove that H is a subgroup of G, right? To prove that H is subgroup of G. H is subgroup of G, right? So here first is existence of identity. Existence of identity, right? So we have here for A belongs to H, A inverse belongs to H, which implies by closure property A into A inverse also belongs to H. But A into A inverse, it means what? Identity. So identity element belongs to H, right? Here identity element is belongs to H. Now therefore the identity is an identity element of H. Now existence of inverse. Yeah. Existence of inverse. Existence of inverse. So for A be any element of H and EB belongs to H. E belongs to H, which implies E into A inverse also belongs to H, which implies A inverse belongs to H. So inverse exists in H, right? Next is closure property. Third, yeah, closure property. We are going in different way. Whatever it is given to you, by using that we will prove the other properties. Closure property. For that, let AB belongs to H, right? Now, which implies AB inverse also belongs to H, as inverse exists for every element, right? AB inverse belongs to H, which implies here A comma B inverse also belongs to H, not A into B. A comma B inverse belongs to H. But here A star B inverse of inverse. हम लोग क्या कर रहे हैं? A भी H में है, B भी H में है, right? It is given that if A and B are in H, then AB inverse belongs to H. A star B inverse also belongs to H. So here the second element is itself a B inverse. So we are taking inverse of second element again. So A star B inverse of inverse belongs to H. But A star B inverse of inverse, it means B, belongs to H, right? So fourth property, associative property. Associative property, right? Elements of H are also the elements of G. Also the elements of G. The composition star in G is associative. Hence, now all the properties are satisfied here. Hence, H with respect to the operation star is subgroup of G star. Subgroup of G star. देखो हमने कैसे prove किया है? Right? So I'm again explaining here sufficient part. If G star is a subgroup and H is a subset of G, then H star will be a subgroup of G if and only if for all AB belongs to H, which implies A star B inverse belongs to H, where B inverse is the inverse of B in G. Okay, so if H star is a subgroup of G star, then H star itself is a group, and if B belongs to H, which implies B inverse belongs to H, also AB belongs to H, AB inverse also belongs to H, so AB inverse belongs to H, which implies A star B inverse belongs to H. Hence for AB belongs to H, A star B inverse also belongs to H. Now the sufficient part here, now it is given that conversely for AB belongs to H, AB inverse also belongs to H. Now to prove that H is a subgroup of G, first one is existence of identity. It means we have A belongs to H, A inverse belongs to H, which implies A star A inverse also belongs to H. So which implies E belongs to H. which implies existence of inverse for A in H and E in H, which implies E star A inverse is belongs to H, and hence it is A inverse belongs to H. Okay. Now closure property. Let AB belongs to H, which implies AB inverse also belongs to H. So A star B inverse of inverse is also belongs to H. So which implies A star B also belongs to H. And hence fourth one, associative property. The elements of H are also be the elements of G. The composition star in G is associative. Right? The composition star in G is associative. Now, hence H star is a subgroup of G star because H is itself a group, right? H with respect to star is itself a group. Hence, H star is a subgroup of G star. Okay. Now, next we will see third one. Now, here we have to prove that. Now, see, it's a very simple example actually. That I is a group set of integers. So I is a group of integers under addition, as we already proved in the last lecture. Right? Set of integers is a group with respect to addition, and H is a subset of integers consisting of all the multiples of a positive integer m. That is H is equal to and so on m0, m2, m and so on. It means it is a multiple of 2, multiple of m. Show that H is a subgroup of I. Okay, here show that H is a subgroup of I. Show that H is a subgroup of I. Now to prove that it is a subgroup of I, we have to take, it means either we will prove here H is a subgroup of I by definition H with respect to the given operation addition is also forms a group, or otherwise we will use the criteria for AB belongs to H, AB inverse also belongs to H, then it's also prove that H is a subgroup of I. Okay, so let's start. As H is a subset of I, as H is a subset of I, to prove that H is a subgroup of I, to prove that H is subgroup of I, as I told you, there are two ways to prove that it is a subgroup of I, right? Either by definition prove that H with respect to addition is also forms a group, or in other way you can prove that for AB belongs to H, AB inverse also belongs to H. So we will prove in a other way. Okay, so that is criteria, by using criteria. So it's very simple. So for here, for all AB belongs to H, okay, we have to prove that here for AB belongs to H, we will prove that here A plus, now it's inverse. Now here operation is addition. So what is the inverse of B here? See the criteria, we will use here the criteria, this criteria. For AB belongs to H, AB inverse belongs to H, A with respect to star, right? But here star is, it means what? Here star operation is given at addition, right? So what is the inverse of, additive inverse of this element B? So additive inverse of this element is minus B, right? This is, we are taking it here additive inverse. So A plus minus B is also belongs to H. We have to prove that this. Okay. So for that, so how we can write the elements of H is here? Elements of H is in multiple of M, right? As for A belongs to H, so we can write A is equal to K1M and B is equal to K2M because every element of H is in multiple of M, right? So we will take this. So which implies here A it means K1M plus B it means minus K2M, so which is equal to here K1 minus K2 into M. As K1, K2 belongs to set of integers, here M is a any integer. So as K1, K2 belongs to H, so here integer. So K1 minus K2 is also a integer. Okay. So K1 minus K2 is also a integer. As K1, K2 belongs to I, so K1 minus K2 is also belongs to I. Right? Now, so as it is belongs to I, which implies which implies k1 minus k2 is an integral multiple of m. K1 minus k2 is integral multiple of m. K1 minus k2 is integral multiple of m, and hence, so k1 minus k2 into m belongs to H, because every element which is multiple of m is present in H. So which implies H is subgroup of I. Here we have used here the second criteria. If instead of using the properties of groups, we will use here the second criteria to prove that it is a group. It means for any two elements belongs to that set H, then AB inverse also belongs to H. In the same way, here addition star is the addition operation, so additive inverse we will take. If here is star multiplication operation, then we will take the multiplicative inverse, right? So I hope it is clear to you how to prove that. Now next point is cosets. So what do you mean by cosets? See here, and one more thing I'm going to tell you here. See, union of any two subgroups. So here union of any two subgroups is not necessarily a subgroup. Okay, union of any two subgroups. Here we will prove, complete the proof. Here we will prove union of any two sets, any two subgroups is not necessarily a subgroup. This is very, very important. Necessarily a subgroup. Okay, I'm proving you here with the help of example. See, the necessarily it is not a subgroup. So union of any two subgroup is not necessarily a subgroup. Okay, now if you take, suppose H1 is the group. So for example, G be the additive group of integers. Okay, be the additive group of integers. G is additive group of integers of integers. Okay, now we'll say that any two sets, that is H1 and H2. Then H1 is equal to here. Then H1 is equal to, we can say that here -4, -2, 0, 2, 4, 6, and so on. H2 is equal to, and so on, -6, -3, 0, 3, 6, and so on. Right? Are any two subgroups of G? Are two subgroups of G. We have to check whether this union of these two subgroup is subgroup or not. Are subgroups of G. Okay. Now we'll take the union. H1 union H2. It will contain the elements -6, -4, -3, -2, and so on. 0, 2, 3, 6, 4, 6, and so on. Okay. As 2 belongs to H1 union H2 here, and also 3 belongs to H1 union H2, right? But 2 plus 3 additive groups, na? G is additive group of subgroups here. G is additive group of integers. So union H1 is also a additive group of integers. So H1 union H2. It means 2 belongs to H1 union H2, 3 belongs to H1 union H2. But if you take 2 plus 3, which is equal to 5, it does not present in H1 union H2. Hence, H1, it means it is not closed. If you take any two elements, the first property fails. If you take any two elements from that set, to say that it is a group or subgroup, first of all, it must satisfy the closure property. So here I am taking 2 and 3 for these two elements from union of H1 and H2, right? So these two belongs to union of H1 and H2, but addition, because addition is defined operation. Now, G is the additive group of integers, so it means addition is the operation. So if I take any two elements and addition of these two elements is equal to 5, but 5 is not present in union of H1 and H2. Therefore, H1 union H2 is not closed, which implies union of any two subgroups is not necessarily a subgroup. Okay? So therefore, union of any two subgroups is not necessarily a subgroups, not subgroup, right? This proves by using with the help of example. Okay, and intersection. So you can, I'm adding one slide here. Right? So in union of any two subgroups is not necessarily a subgroup, but intersection of the arbitrary intersection of subgroups, arbitrary intersection of subgroups, arbitrary intersection of subgroups of a group, a subgroup. Means intersection of any two sets is again a group, but subgroup, but union is not necessarily. Suppose we'll say that let G star be a group, yeah, group. Okay. And H1 H2 and up to Hn, H1 H2 up to Hn are subgroups of G, right? Are subgroups of G. Then we have to show that. Then to prove that, what we have to prove, that intersection of arbitrary intersection of this set is also a subgroup of G. It means H1 intersection H2 intersection H3 and so on intersection of Hn is also a subgroup of G. Also a subgroup of G. Therefore, H1 intersection H2 intersection H3 and so on intersection of Hn is equal to intersection of Hi, I varying from 1 to n. Okay, I varying from 1 to n. So we will take two elements. Let A belongs to, okay, let A belongs to intersection of Hi. Okay, where I is varying from 1 to n, and B belongs to intersection of Hi, right? Any two elements from the intersection, arbitrary collection of an intersection of sets. So which implies as A belongs to Hi for all I belongs to natural number set, and B belongs to Hi for all I belongs to natural number set, right? B1, B2, B3 and so on. So which implies A star B inverse by our criteria of subgroups. A star B inverse also belongs to Hi for all I belongs to N, right? A star B inverse is also belongs to Hi, because if you take any two elements, A B belongs to H, then A star B inverse is also belongs to H. So similarly here, A belongs to Hi and B belongs to Hi, then A star B inverse is also belongs to Hi. So which implies intersection of I varying from 1 to n, Hi is also a subgroup. Hi is a subgroup of G. Okay. Hence, arbitrary collection of or arbitrary intersection of any subgroups is also a subgroup of G, but union of any two subgroups is not a subgroup of G. Right? Now, next is cosets. Next property is cosets. Now, what you mean by cosets? We'll see. Let G star be a group and H be any group of G. Let A be any element of G. Then the set H star A. Okay, left coset. It is known as it is known as right coset. H star A is equal to H star A such that H in H is called a right coset of H in G generated by A. Here A is the generator. Similarly, the set A star H is equal to A star H, where H in H is called the left coset of H in G. Okay, this is called as left coset of H in G. So if G is abelian group, then left coset is equal to right coset. If G is abelian group, then we have left coset, right coset is equal to left coset of H in G. Okay. Now, so we can see that, for example, what we mean by left coset. Let G be the additive group of integers. G be the additive group of integers, then let G be the additive group of integers. We'll see. Let G be a additive group of integers. So we have G is equal to -2, -1, 0, 1, 2, 3, and so on, right? And H be a subgroup of G. And H be a subgroup of G, right? So we can write H as here -10, -5, 0, 5, 10, 15, and so on, multiple of 5. Okay. And let 1 belongs to G, right? 1 belongs to G. Then we have here 1 belongs to G, then we have H plus 1 is equal to, and so on, -9, -4, 1, 6, 11, and so on, right? H plus 2 is equal to, and so on, -8, -3, 2, 7, 12, and so on, right? So 3 belongs to, this is your C. If you add right, so this is your right coset. Okay. And these are the pairwise disjoint. Okay. Similarly, for 3 belongs to H. So we have H plus 3, -7, -2, 3, 8, 13, and so on. Right? For 4 belongs to H. So we have H plus 4 is equal to -6, -1, and so on. Right? So H plus 5 is equal to -5, 0, 5, 10, and 15, and so on, right? So now H is equal to H plus 5. So you will get H, comma, H plus 1, H plus 2, H plus 3, and so on are pairwise disjoint. Are pairwise disjoint. Hence, these are the right coset of H in G. Okay? Right coset of H in G. Okay, I hope it is clear to you what we mean by coset. Okay, now here we have one theorem. If H is a subgroup of G star, then and H belongs to H, then H star H is equal to H star H. It is for a subgroup, left coset is equal to right coset. Okay. So the next important thing is that order of an element. Order of an element. Yeah. Definition, let G dot be a group. Okay, G dot be a group. By the order of an element A belongs to G. Okay, by the order of an element A belongs to G is mean that the least positive integer n, if one exists, such that A raised to n is equal to identity. If there exists no positive integer n such that A raised to n is equal to identity, then we say that A is of infinite order, of order, or of order 0. Okay. Now suppose for example, set of integers with respect to addition is a group of infinite order. There does not exist any particular integer n such that a raised to n is equal to identity. Therefore, set of integers with respect to addition is a group of infinite order. Are you getting it? We cannot find out any n, least positive integer n, such that it will generate all the elements of integer. So this is I plus is a group of infinite order. Okay. Now next, here, for example, one more thing, 1, 2, 3, 4. With respect to addition, with respect to multiplication modulo 5, is a finite group of order 4. The finite group of order 4. Now, for that we have to find out the order. For that you have to prepare the composition table for this multiplication modulo 5. Okay, and you can find out the order of the element, each element of order. So 1, if you multiply 1, 1, 1 4 times, it will gives you the identity element, right? If you multiply 2, it means here see 1 into 1 into 1 into 1. The order of that element is 4, right? So 2 into 2 into 2 into 2, multiplication modulo 5, na? So here 2 into 2 into 2 into 2, 4. So 2 to the 4, 4 to the 8, 8 to the 16. And when divided by identity element, we require the identity element. So here 15, 15 when divided by 5, it will give you a remainder 1. It means 2 raised to 4 is equal to 1. Right? Exactly similar way. Here 3 raised to. So 3 into 4. So here smallest least positive integer n is 4. Right? So here 1 into 1. So you will get 3 into 3 into 3. 3 3 is a 9. 9 3 is a 27. 3 is a 81. So it will gives you 1. Right? So it will gives you 1 when divided by 5. So here here 1 into 5. So 5. So 1 raised to 5 is equal to, will get 5, or 1 raised to 1 is equal to 1. So least positive integer here you are getting 4. So 3 raised to 5 is equal to 1. That is identity element. Okay. So identity element multiplication modulo 5 with respect to multiplication modulo 5 for this elements is 1. So 3 raised to 5. In the last lecture I have told you, covered everything, how to find out the multiplication modulo 5. Okay, multiplication modulo n, addition modulo n, and congruent modulo n. Each type of example I covered in that lecture. You go through it so that it will, this step you will get clearly. Okay. Now here 3 raised to 5 is equal to 1. Exactly 4 raised to. So 4 raised to 4. 4 raised to 3. So 4 into 4, 16 into 3, 4 in, so 16, it means 4 raised to 2 is equal to, when the multiplication modulo 5 is equal to 1. So this is the finite group of order 4. Okay. Now, so 0, 1, 2, 3 is a finite group of order 5. So this is, we will get it. Now next is suppose. Now we'll take one example. So G is this is different group. G is equal to 1 minus I plus I minus I. Right? It's a group with multiplication. The group with multiplication. We can show that here. With multiplication. Okay. If you want, you can find out the composition table. 1 minus 1 I minus I, 1 minus 1 I minus I, right? 1 into 1 1 minus 1 I minus I, here minus 1 plus 1 minus I and plus I, right? Here I minus I minus 1, I square is minus 1, and minus of minus 1 is again plus 1. So minus I plus I plus 1, and minus 1 is plus, so minus 1, right? So so obviously it is a group. G is a group with multiplication. Now see, every element has a composition table, all the entries from the composition table from the set G only, therefore G is closed with respect to multiplication, right? And here associativity also holds, so can take 1 into 1 into minus 1 is same as 1 into 1 into minus 1. Okay, so which element acts as an identity element? 1, because 1 gives you exactly similar row. So 1 belongs to G, acts as an identity element, and inverse exists for every element. Inverse of 1 is 1. Inverse of minus 1 is minus 1. Inverse of I is minus I, and inverse of minus I is I. So inverse exists for every element. Therefore, G is a group with respect to multiplication. Now we will find out order of every element. So what is the identity element for this group G? 1. So we have to search the least positive integer m. The order of every element, not we have to find out the order of the group, this set G. We are going to find out order of every element of this group. So 1, order of 1. So how many times I have to multiply 1 with itself to get the identity element? Only 1. Okay, so order of 1 is equal to 1. Now how many times I have to multiply minus 1 with minus 1 to get the 1? 2 times. So minus 1 into minus 1 is equal to 1. Therefore order of minus 1 is equal to 2. Are you getting it? The least positive integer n is 2. Right? Now here order of the minus 1. So order of here how many times I have to multiply I with I to get the order to get the identity element 1. Now I into I square is equal to minus 1. So into minus 1 into I is minus I, and again into I. That elements I have to multiply that element with itself to get the identity element. So how many times I have to multiply this? 4 times. Multiply I with I 4 times to get the 1. See, I square is minus 1, I square is minus 1, and minus 1 into minus 1 is plus 1. Therefore, order of I is equal to 4. Are you getting it? Now, here minus I. How many times I have to multiply minus I here? So you can see here minus I. So order of minus I is means minus I into minus I. So plus I square and minus 1. So minus I into minus I again. 4 times I have to multiply. Minus I into minus I plus I square. I square is minus 1 and this minus 1 becomes plus 1. So therefore order of minus I is equal to again 4. Now if you observe here, order of 1 is equal to 1. Order of minus 1 is equal to 2. Order of I is equal to 4. And order of minus I is equal to 4. I hope you are clear how to find out the order. Now it is depending upon the operation, which operation is defined. Here is dot. So we are taking dot operation. In the previous example here multiplication modulo 5. So we are taking multiplication modulo 5. How many times I have to multiply 1 with 1 and after that divide by 5 to get the remainder 1. Okay, that will be the order. Now here is also same. Okay, so next is cyclic group. So to learn cyclic group, you must have to learn the order of the group first. Okay, that we have seen how to find out the order of an element. Now, a group G is called a cyclic group if for some A belongs to G. If for some A belongs to G, every element X in G can be written as A raised to M. Cyclic group. So there is a cyclic. So every element of the group G can be generated by a single element. It means here we can say that every element of this group can be generated by the same elements. It means if you take I, so I and minus I are the generator here. In this example, so we can see here. So that is every element of the group G can be generated by some element of G. So such groups are known as cyclic groups and element A is known as generator of the group G. And G can be expressed as generated by A. Here G is a generator, A is a generator of G. This can be denoted in this way. Now for example, just now we have seen one example here, 1 minus 1 I minus I. This is the group with respect to multiplication. Now see, check whether there exists an element which generates all the elements of the group G. मतलब वहां पे एक ही ऐसे एलिमेंट्स है, ऐसे कौन से एलिमेंट्स है जो सारे ग्रुप के एलिमेंट्स जनरेट करते हैं आफ्टर मल्टीप्लिकेशन विद इटसेल्फ. Okay, now if I multiply I with I, if I only I with I, then it will be gives you here I with I, that is I square. I square is equal to minus 1. So minus 1 is generated by I. Okay. So I into I into I. So it will gives you I square is minus 1 into I, that is minus I. So I generated by minus I generated by I. Now I with I with I with I. So it will gives you I raised to 4. I raised to 4, it means I square is minus 1. This I square into I square, which is minus 1 into minus 1. Minus 1 into minus 1 is plus 1. Right? So see here, minus 1 minus I and I is generated. So I have to multiply I with only one time. I, right? I with itself. That is I. So every element is generated by I. Similarly, we can take the minus I also. So how many generators for this group G have? Now this is I. So therefore, I is generator of group G. Right? So I is a generator of group G. Similarly, you can say the minus I also. Minus I into minus I. Minus minus plus I square is minus 1. Right? So minus I into minus I into minus I. I square is minus 1 and this minus I. So it will gives you I. So minus I into minus I into minus I into minus I. So this is minus minus plus 1. I square is minus 1 and here is also minus 1. So this will give you 1. And I with itself. So minus I. So I and minus I are the generators of this group G. So we can define here G is generated by I and G is also generated by minus I. So if you multiply 1 with itself, it will give you only 1. Minus 1. So it will not give you 1 and minus 1 are not the generators of the group G. Why? Because whatever times of 1 is multiplied with 1, minus 1 is multiplied with 1, it won't be gives you the I and minus I. Right? So therefore 1 and minus 1 are not the generators of the group G. Here I and minus I are the generators of the group G, because when you multiply that element with itself, it will gives you the every element of the group G. Therefore, that is called as a generator. So here, G is a cyclic group because there exists a generator. So such group is known as cyclic group. Therefore, G is a cyclic group. I hope you are getting it clearly here what you mean by cyclic group. Right? So if there exists a generator which generates all the elements of the group G, then that G is said to be cyclic group. Okay? Now, similarly, here one more example we can take, the three cube roots of unity. Second example, three cube roots of unity. Cube roots of unity forms a multiplicative cyclic group. Right? It forms a multiplicative cyclic group. So here we can say that G is the cube root of unity. So this is your group 1 omega omega square. And cube root of unity, it means omega cube is equal to 1. Okay. So we can say that now this is obviously this is a group. If you want, you can show with the help of composition table 1 omega omega square. So what omega omega square multiplication with respect to multiplication omega omega into omega omega square omega into omega square, that is omega cube, but omega cube is 1. So here is omega square into omega is omega cube, that is 1. Omega raised to 4. Omega raised to 4, it means I can write omega cube into omega. So omega cube is 1 into 1 omega, it means omega. Right? So this is G is a group with respect to multiplication. Now this is also a cyclic group. Why it is cyclic group? Now if you observe here, omega and omega square are the generators. See, if I multiply omega with itself, so, omega no multiplication, so only omega it will gives you the 1. So how many times I have to multiply omega with omega to get the identity element? Identity element of this group is 1, because 1 gives you the exactly similar row. So 1 is the identity element. So I have to multiply omega with omega with omega 3 times. Omega cube, because omega cube is equal to 1. Right? Now, how many times I have to multiply omega with, see here, omega into omega into omega into omega. So omega cube is identity, right? And into omega, it will gives you omega. Now, omega into omega into omega into omega into omega. So this omega cube is identity into omega square. So omega. So every element is generated by omega. Yes. So omega is the generator of group G. Right. Similarly, omega square also we can see that omega square into omega square. It means omega cube. Omega raised to 4. But omega raised to 4, you can write omega cube into omega. So the omega cube is 1. So here is omega. So omega square generated omega. Now omega square into omega square into omega square. So here is omega raised to 6. But omega raised to 6, you can write omega cube into omega cube. So that is 1 into 1, which is equal to 1. Right? Now here omega square into omega square into omega square into omega square. So it will gives you omega raised to 6, it means 1. And into omega square, it means omega square. So omega and omega square are the generators of this group G. Therefore, G is a cyclic group. If there exists at least one generator who generates every element of the group G, then it is a cyclic group. I hope it is clear to you. G is a cyclic group. Okay, and one more thing is that every finite group is cyclic. Okay, as this is finite group, therefore it is cyclic. So every finite group must have to remember here, remark, every finite group, can say that every finite group is cyclic. Okay, every finite group is cyclic. So yeah, now some properties of a group. Every prime order, every group of prime order is cyclic. Okay. So every group of prime order is a cyclic. It means there exists a generator. Okay. So for that here we have to say that the Lagrange's theorem. So what do you mean by Lagrange's theorem? The order of, we will do that here. Lagrange's theorem is very important theorem in a group theory. Okay. Here is Lagrange's theorem. The statement is the order of each subgroup, the order of each subgroup of a finite group, a divisor of the order of the divisor of the order of the group. The order of each subgroup of a finite group is a divisor of the order of the group. Okay, so this is your Lagrange's theorem. So for to prove that every group of prime order is cyclic, we will use it here, Lagrange's theorem. Okay, prime order, prime number, it means what? An integer p is said to be prime if p is not equal to 0 and p is not equal to plus or minus 1, and only the divisors of p are plus or minus 1 and plus or minus p. Then least positive integer, the least positive prime number is true. So we will start with that, least positive in prime number. Okay. So suppose G is a finite group. Suppose G is finite group whose order is a prime, whose order is a prime for P. Then we have to prove that. It is a cyclic. Then we have to prove that G is cyclic. Okay. We have to prove that G is a cyclic group. Okay. Now, at least positive prime number, least positive prime number is P. The least positive prime number is 2. The order of G is at least 2. Okay. Hence, there exists A in G such that A is not equal to E, such that A is not equal to E. Also order of A is greater than or equal to 2 as only identity element. तो वैसे कौन सा element है जिसकी order greater than or equal to 2 है? As only identity element of order 1. Right? So 1 is the identity elements. We don't have to multiply 1 with how many times? Only 1 is the identity. So order is 1. Okay. Order of that element is 1. Now, next is here we can see that. So let suppose order of A is equal to M. Then H is generated by A. It means A raised to M is the identity. Right? So is a cyclic. It's a cyclic subgroup of G, and order of H is equal to order of A is equal to M. Therefore, by Lagrange's theorem, we have M must be a divisor of here you will get P, right? But P is prime. Where M is greater than or equal to 2. Hence M is equal to P. Therefore H is equal to G. This H is cyclic, therefore G is cyclic. Since H is cyclic, or G is cyclic. H is cyclic, therefore G is cyclic. Okay? So every group of prime order is cyclic. Now every cyclic group is an abelian group, and now just we have to prove that every group of prime order is cyclic and every cyclic group is an abelian. As we know that here, let G be to prove that it is an abelian. So as it is a cyclic, let G is generated by A. As it is a cyclic group, so there is a generator. So as G is generated by A, be a cyclic group. Right? Be a cyclic group generated by A. Let X and Y. To prove that it is an abelian group, we have to take two elements, X and Y, and prove that X into Y is same as Y into X. So, next is here X and Y belongs to, let XY belongs to G. Okay. So, as it is generated by A, so there exists some integers, then as G is cyclic group, right? As G is cyclic, so every element can be written in the form of generated by A, right? So there exist integers R and S such that here we will get X is equal to A raised to R and Y is equal to A raised to S. Now here X into Y is equal to A raised to R into A raised to S, which is equal to A raised to R plus S, right? So which is equal to A raised to S plus R. so which is equal to a raised to s into a raised to r, so which is nothing but y into x. So therefore every G is an abelian group, right? Therefore G is an abelian group. Hence every cyclic group is abelian. Yeah, every cyclic group is abelian. Now next is normal subgroups. What do you mean by normal subgroups here? Let G star be an abelian group and H star be any subgroup of G. Then left coset of H in G and right coset of H in G is equal to left coset of H in G. That is for all A belongs to G. However, it is possible that G is not an abelian group. It possesses a subgroup such that H star A is equal to H star H for all A in G. Such subgroup H of group G is known as normal subgroup of G. Okay, now one more definition is also there for the normal subgroup. Now see a subgroup H of G, we will use this definition, normal subgroup. See a subgroup H of group G, subgroup H of group G star is said to be a normal, normal subgroup of G, said to be normal subgroup of G if for all G in G and for all H in H. G star H star G inverse also belongs to H. जो हमें प्रूव करना है नॉर्मल, उसका एलिमेंट बीच में आएगा, रिपीट इन माइंड ऑलवेज. और जिसका प्रूव करना है वो राइट, लेफ्ट एंड राइट में आएंगे, राइट. So H is a normal subgroup of G. It means for all G in G and H in H, G star H star G inverse belongs to H. Now see here, quotient groups are also there. See, G be a group, say that quotient group. Let G star be a group. Let G star be a group. Let N star be a normal subgroup of G. Be a normal subgroup of G. If A belongs to G, then N star A is right coset of N in G, right coset of N in G, also N being normal subgroup of G. Each right coset of N in G will be a left coset of N in G. Here, left coset of N in G. Okay. So G by N, the quotient group G by N, you can see that here N star A belongs to G. So G by N is called quotient set. By N is called quotient set. Next is homomorphism of groups. Okay. Most important definition, that is homomorphism of group. Here G composite be a group and G dash star be another group. Then the mapping F defined from G composite to G dash star said to be homomorphism if F composite A, it means F operated on this set, right? It means here F defined from G composite to G dash star. So it means here F operated on this, so F of A composite B, so is equal to F of A star F of B. Okay. If here is addition, suppose F defined from G plus to G dash dot. Then here you can say that f of a plus b is equal to a into b. F of a into f of b. Right? That way. Now, yeah, that is here we can say that. So suppose this is your group. So most of the time the definition will ask you mean by homomorphism. So here is G composite be a and G dash star be a. Here I've defined from this A B A composite B. Here A dash B dash and A dash is your composite. This is homomorphism of a group. Next, isomorphism of groups. F defined from G composite to G dash star. Let F from group G composite to G dash star is a mapping such that F composite B, F of A composite B to F of A star F of B, and also F is one and onto mapping, then F is known as isomorphism from group G composite to G dash star, and groups G and G dash are known as isomorphic groups, and it is denoted by isomorphic to G dash. Okay, now endomorphism, an isomorphism from homomorphism from group G to itself is called endomorphism. Definitions: a homomorphism from group G to itself is endomorphism. That is F defined from G composite to G composite such that F of here small f, F of A composite B is equal to F of A composite F of B. Then F is known as endomorphism. Okay. Then F is known as endomorphism. Next, here automorphism of a group. So automorphism, it means isomorphism F from group G to itself is known as automorphism. It is F is one on 2 and if preserves the F preserves the composition. Okay, then F is known as automorphism of the group G. Now, here, for example, let G be a group with identity element E. Then show that the function f defined from G to G defined by f of A is equal to E for all A in G is a homomorphism. Prove that it is an homomorphism. Now, see, f defined from G to G and f of A is equal to identity. It is defined as. So for all A in G. To prove that homomorphism, we have to take two elements from G. So let A, B belongs to. Now consider here then f of A into B because here multiplication, right? So if it is not given, so by default multiplication is operation. So when AB belongs to G, as G is a group, then it means A into B is also belongs to G. So f of A into B is equal to defined as the identity for all AB in G. So identity element. So this can I write identity into identity, but this identity is nothing but f of A, and this identity is nothing but f of B. So f of A into B is equal to f of A into f of B. Therefore, F is homomorphism. Therefore, F is homomorphism. Okay. So I hope you are getting it clear what you mean by homomorphism. And then Cayley's theorem is there depending upon the homomorphism. So every finite group G is isomorphic to the permutation group. Okay. Just write on the statement Cayley's theorem. Every finite group G, every finite group is isomorphic to is isomorphic to a permutation group. Is isomorphic to a permutation group known as Cayley theorem. Okay, every finite group G is isomorphic to permutation group. You have to remember just statements and you can prove that this is also isomorphism. Now kernel of group homomorphism. Find only the definitions. Kernel of group homomorphism. Kernel of group homomorphism. Okay. Definition: F if F is a homomorphism from group G star into a group G dash composite, G star into dash composite, then the set K of, then the set K of all those elements of G, all those elements of G which are mapped by, which are mapped by F on the identity E dash, identity E dash of G dash is called kernel homomorphism. Is called kernel homomorphism. Okay. For example, diagrammatically, suppose this is your with star, your group dash is composed. Okay. So here f is a function from star to G dash composite. And f is homomorphism when every identity element mapped to the identity, right, called as kernel of homomorphism. Set of all those elements. Kernel of homomorphism. Right? Here kernel of homomorphism, where set of all those elements which maps to the identity element of, or in short we can say that A belongs to B such that f of A is equal to E dash, where E dash is an identity element of G dash. E dash then identity element of G dash. Okay? E dash is an identity element of G. That's it. The kernel of homomorphism. Okay. Next, we will see the next point. I think I covered most of the terms here, which is very important in the group theory, is subgroups, then Cayley-Hamilton theorem, automorphism, homomorphism, quotient group, normal subgroups, everything I clear here, cyclic groups, everything is covered, order of an element and cosets and arbitrary union or arbitrary intersection of an subgroups is again a subgroups, and union is not necessarily a subgroup. So every part is covered over here. So I hope you are getting it clearly and every concept of the group theory here, so that you will get definitely your doubts will be clear from the group theory from the yesterday's lecture and from this lecture. So I completely cover most important things from the group theory. Okay, so I hope you are liking it, and if you really like my videos, please do like, share and subscribe. And one more thing, tomorrow I will be here at the same time from 11:15 with the new point of ring theory. Okay, so your every concept will be clear of ring theory tomorrow at the same time. And one more thing is I'm telling you here that I will be available from Monday at the same time on Unacademy's semester channel, okay, semester exam channel.